Bismillah ar-Rahman ar-Rahim. Wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. So in this lecture we will apply the concepts of gradient descent and convex optimization into a real prediction problem. And we will consider the California housing dataset. It's a known dataset to build predictive models. And the first cells of the notebook, we will load this dataset and we make simple descriptive statistics. So this dataset contains several features, and the objective is to predict the target value will be the house valuation or the house price, okay, med house value. So we want to build a predictive model that will take all these features as an input feature X and try to predict the value of the house price. So we load the data, and then you can go through the descriptive statistics to find the averages, the standard deviation, and other information about these data. So we will select the features. What are the features here? All columns except the last one. Zoom in. Okay, so we have housing DF. So we can select features from the data set. House ages and average rooms. Average bedrooms. Of course, you can do also PCA if you want to select the most representative ones, but now this is not the purpose. But usually if you want to do a real predictive modeling, you need first to make sure that all these features are not correlated with each other and remove the correlated features in advance. Okay, we can select certain number of features, and the output variable will be housing DF, the last column, and will be the median house level, this one. Key errors. Okay, yes. It must be between brackets. So I need to add a bracket here and a bracket here.
Now, why does it need only three features?
It's a choice. It's a choice. It is a choice. Okay, so we consider only these features.
Can I go with them?
Huh?
Can I go with them?
Yes, but I told you, in principle, we should analyze the covariance between the different features and make the PCA. But in this simple example, our objective is just to build a predictive model. So we select only three features. Our objective is to build a linear regression model. So we will make an assumption that there is a linear relationship between the three features and the target variable, and we will build a model based on this. So this is how we will work on the model. Look, we will try to formulate a linear combination between the med house value, okay, which is a weighted combination of the three values, W1, W2, and W3 plus B. What is the objective here?
Find the weights.
Is to find the weights that,
Give us the best prediction for the med house.
yeah, that minimize the loss. What will be our loss function here? The mean square error. It can be also the absolute error, but we will use the mean square error as we did in the lecture. Is it clear? So this is a problem formulation. We start from an assumption that there is a linear combination between the three features and the house price. Okay, maybe this assumption is not correct, but how do we know whether it is correct or not? We will check if the MSE is very high or is reasonable. Okay, maybe there is a more complex feature or maybe a more complex pattern. So we need to find the best W1, W2, and W3 that are the weights of each feature, and B is the bias that we will add. And our objective is to implement the model in Python and define the loss function, which in our case will be the mean squared error, apply the gradient descent algorithm to optimize the loss function, and finally evaluate the model. Yes?
Doctor, how do we know which loss function to implement? Is it which one we like more? What the loss function?
No, I mean, it depends on the problem. Usually in logistic regression, and we explain this, so we need to calculate the difference between the prediction and the actual value. Yeah, so if you make y predicted minus y actual, you may have negative values. So either you do the absolute value, which is the absolute error, or you multiply by the square to always have a positive value for the error. So they will sum up, okay? They don't reduce over time, over the epochs. So the first thing in our case, we will start from initial weights. How do we initialize the weights? How did we learn that we initialize the weights? We put them to 0. W equal to 0 and B equal to 0. This is what we have done, right? So we initialize all the weights to 0. W1 equal to 0, W2 equal to 0, W3 equal to 0, and B equal to 0. This is what we call zero initialization. A better one is to make random initialization, but not completely random. Okay? So we will initialize the weights randomly using a normal distribution where the mean must be equal to 0. It's like standardized. Okay? We don't want to have a mean that is, for example, equal to 1 or 10 or so on, because we can have issues about the stability of the training. So the mean will be around 0, and here the variance will be 1 divided by the number of features. I have 3 features, so the variance 1 divided by 3. This is a known initialization called Xavier initialization. It's used in deep learning, and it was shown to provide better conversions and faster conversions of the predictive algorithm. Okay, there are research papers, I think from 2015, Xavier initialization, that was proven to be much better than zero initialization or completely random initialization. So we will use the normal distribution or the Gaussian distribution to initialize the weights to random values while respecting this distribution, the normal distribution. So the key benefit of the Xavier distribution: maintain consistent values across the layers. Okay, if you have multiple layers, here you have only simple layers. Prevent vanishing gradient and exploding gradient. So what does it mean, vanishing gradient and exploding gradients? When you calculate the gradient, if you obtain very large values, so it will compromise the stability of your computation. Okay, you may go to infinity. Or if you have very small values, you may end up by not updating the weights. So we want to avoid extremely low values and extremely high values. This is why we will keep always the weights distribution around, okay, controllable variables. We usually use different type of normalization to avoid this problem, especially in deep neural network where we can have unstable computations. Now you have a function which is called initialize parameters, and the initialization can be set either to Xavier or to 0. And this is the number of features. So what you will need to do, you need here to complete the code by, if the initialization is equal to Xavier, you will initialize the weights according to the Xavier distribution method, or if the initialization is set to 0, you will initialize. So this is going to be simple, we will put here 0 and 0. Okay? So try to complete the Xavier initialization. Take some time and complete the Xavier initialization. So just to summarize the solution, we calculate the standard deviation np dot square root of 1 divided by the n features. This is by definition. We use np.random.normal and 0 mean, standard deviation that we calculated here. And this is a vector of n features. We have 3 features in our case, W1, W2, and W3. The bias is initialized to 0. In case of 0 initialization, we will use np.0 to initialize the vector of 3 elements, and the bias is equal to 0.0. Now you can test. We will create 5 features. Just this is the testing, and you'll use initialize parameter with 5 features and Xavier here. And in the second case, we will use 0 initialization. So you will see the difference here. Look, these are the weights. Yes. If you calculate the standard deviation of these 5 values, it will be 0.28. And 1 divided by 3 is 0.33. So it's close. Voila. Okay. And the expected standard deviation is 44. We have 5 features here. 1 divided by 5. 1 divided by 5. It's the NP SQRT. Okay. Yeah. It's not the variance. Okay, if I choose 10 features, of course, if I make the standard deviation of 10 features, is going to be closer because the sample size is small. Okay, look now, 0.21 is equal to 38. Yes?
Isn't it supposed to be random weights?
Yeah, these are random weights now.
Why did we both get the exact same weights?
It's because of the seed. Now, if you change the seed value, okay, because usually random number generators start from a value and then there will be a sequence. It's already a static sequence, which is random. But if you start from the same seed, you will have the same static random sequence. So if you change the seed, you will have another sequence. Okay? So now, if I change the seed, it's completely different. And you will see you will have also different standard deviations. Is it clear?
Yes.
Okay. Now, the next step, we have initialized our weights. We need to create a function that calculates the loss. Okay? The MSE is defined as the average of the predictions squared. The difference, the error of the predictions with the actual value, and you make the square. So try to complete the MSE value here. It's a very simple equation in NumPy. So take 1 minute and try to find the solution. So as already explained, we need to implement this in Python, so we can see it in two different ways. I can consider 1 divided by n, the sum, as the average of this quantity, or I can consider the sum of this quantity as a dot product of the error by itself. You know, x squared in the vector space is the dot product of x by x. Okay, so different ways on how to do that. So let's start with the simple way. We can use mp.mean. Okay, we will use, so what do we have here? Y true and Y pred. Y true minus Y pred. I can do multiplied by Y true, and we can do like this, or you can do just exponent, yeah, of 2. Yeah.
Does it matter which one you put for predicted?
And you, sorry?
Does it matter if they want to for predicted?
No.
Just the difference.
Yeah. Square. The second way, what we can do, is to make mp dot this is the error. Yeah, I can do error equal divided by, yeah, the length, or so it's a NumPy, so we don't do the length, we can do y through the size. Huh? Yeah, it can also be errors. Dot size, same thing. Sorry? Yes. Okay, that's fine. So both are possible. You can use this formula or the other formula.
And I think that you can also use library, like skikit, the main import plugins.
Yeah. Now we want to build everything from scratch.
Yeah.
There are, later on in machine learning, we will use all the libraries, but you need to understand how these algorithms are really implemented. Okay, this is the objective of today. And now the next step, which is the most important, is the calculation of the gradients, the derivatives. So yesterday we have already introduced how to calculate the derivatives. We will calculate the derivative of MSE with respect to each weight. How many weights we have?
3.
So we'll calculate with respect to W1, W2, and W3, and then we will have also the bias. Okay, the difference is that every weight is associated with a feature, and the bias is not associated with a feature. So all the derivatives of the weights will be the same. It's so this expression, the loss divided by dWg, and will be 2, so because it's power of 2 multiplied by this sum, the sum of the errors, same as we did yesterday. So this is the prediction minus the actual value. Clear? So this is the error, the sum of the errors, multiplied by xg. So here it's the feature related to the weight, because we are deriving with respect to the weight. Okay? This is partial derivative. I think in calculus you made partial derivative of equations. Okay, so this is the feature with respect to wi, because we are deriving with respect to that particular feature. And we do the same thing. Okay, using the chain rule, this becomes as follows. Okay, so we can remove this dw over dg here. And we do the same for the bias as well. So all the objective now is to implement the derivative in the train function. So look at the train function now. we need to understand how the train function works. After calculating the derivatives, we will make the update rule. You know, what is the update rule? Every weight will be equal to the old value minus learning rate multiplied by its derivative. And the bias will be the same. Yes, this is the update rule. So we calculate the derivatives of with respect to each weight, with respect to the bias, and then we update the weights. What will happen when we update the weights? We're going to reduce the loss function. So the next prediction will provide a loss that in principle should be lower, okay, than the previous one. So let's try to implement this.
The weights here, we take it as a whole array, right?
Yes. So the number of samples, we have now feature X and output Y. So X is the feature and Y is the target variable. This is what we want to predict. So the number of samples, this is how many features we have? 3 features. Okay. And the weight and the bias, we will initialize them. So we will call the function initialize parameters. Number of features. So our function initialize parameters, and here we will choose initialization equal.
So number of features 3, right?
Yes, exactly. This is what you have did before, right? So X shape. How many features we have? No, it's not one. Yeah, shape 1, because this is the number of rows, or the number of this will return the number of features.
Doctor, are the features 3?
Yeah, but we're not going. Yeah, we can make it 3 here in this particular case. In this particular case, it's 3. Yes.
Because I think one will give us 0.
So what is X shape here? Just a moment. We have.
Isn't it just one sample?
Just a moment. Yeah, it's only X shape here because the shape will contain both 2 values, the number of samples and the number of features. Yeah, so that's fine. Okay, now we will go inside the training loop. How to calculate Y pred? What is Y pred here?
Predicted value.
Yeah, the predicted Y.
The weights multiplied by
Okay, so the prediction, okay, it's weight multiplied by X plus B. How to do that? NP? Yes? Dot? Yes?
the
Weights?
weights, the X vector,
X? Yes?
and then plus the y.
Plus the bias. Yes, that's good.
It's fine.
Bias, yeah. Okay, how to calculate the error?
Use the LT.
Hmm? Yeah, compute MSE Y, which is the observed value, Y pred. Yes. And then? No, this is the error.
Error is the difference between y and
Yeah, the error is the difference. Now, this is the MSE. The error is Y, pred minus Y. Yes. DW. What is DW? Let's look at DW here. It's what? أنا سويناها من فوق. شوفوا الآن. سويناها في سكالر. DW is equal X multiplied by the error. صح ولا لا? Okay, so we have calculated the error here. So it's equal to 1 error, or okay, MP dot error multiplied by X T. Is it correct? We have to check. Yeah, no, XT multiplied by error. So let's follow the same equation. It's XT t, and here we have the vector errors, and we divide by n and samples or features. Yeah, and samples. And dB is what?
Sum.
1 divided by n, sum of all errors. How to calculate that? It's calculating this, yes. MP dot sum. So here we have updated the gradients. We calculated the gradients. What's the next step? This is the update rule. How to update the rule? Okay, so it's equal weights. Let me make it explicit. Weights minus the learning rate multiplied by dW. And here we will use bias minus learning rate multiplied by dB. That's pretty much it. So this is our training. This is how we'll do the training. Okay? At every iteration, we will calculate the derivative of the loss with respect to each feature, each weight, and the loss will be decreasing toward the minimum value. Okay? This is another function training with threshold. So for this function, we will train for a certain number of iterations or epochs. Now for the prediction, this is simple. Okay, the prediction is x np dot np dot this is xt. If you don't do xt, it will not, because to align with the weight values, with the weight dimension. We will try. If it doesn't work, I'm going to remove it. So sometimes it's because before I tried it without xt and it didn't multiply the np dot product. So how do we know that? You know, it depends on, because I don't have actual values, so I cannot anticipate on this. But anyway, we will change it. So let's try it here if it works. Yeah, it didn't work. So where is the issue? In the train, there is a problem here. Weight x. Look, I didn't put here the t, and it seems like it's having an issue. No, it's here in the dot product. I didn't put here. So this is just to check whether your shapes are correct. Look, now it's working. The shapes are working. شوف الآن at each iteration what's happening for the MSE. Look at the MSE. Start with 43 and then going down until going 0.3. Okay, so you can see the impact of gradient descent and how it can guide the model to reduce the mean square error by using convex optimization technique. Okay, so later on you can just run the model on the housing data set, and you will find, it's not defined. I'm going to make just train. Let's just train it on our data set. MSE threshold is not defined. Okay, because I will use for a certain number of iterations. Let me run it for 10 iterations only. Not sure where this error expected 3 got 2. What is the function train that you've made here?
Because this is with the threshold.
There is y. Let me take all of this.
Use train only without.
This is how we use it. X, y, learning rate, and iterations, yes. Yeah, the final MSE, this one. How many output we have? Train, weight and bias only, yes. We need to return only 2 values. Let me try them. Yes. So after 10 iterations, the MSE is 5. If I make 100 iteration, maybe now the learning rate, okay, 1,000 iteration. So we can see now it's decreasing. Now this is applied on the housing data set. Okay, so this is a model that after 900 iteration it reaches an MSE loss. So we can now take the W and B and make the linear relationship to predict the price of the house based on 3 features from the data set. Okay, with an MSE equal to 0.6.
Is this acceptable number?
We can have better. Okay, now in principle we should go to the testing phase because now we only made the MSE on the training. We need to make on the testing and check if there is an overfitting or there is an underfitting and if these MSE are acceptable. واضح؟ Okay.